All right, everyone. We had some homework due today, assigned on Tuesday. First one was worksheet number 6. We got the answers up. For the first couple of questions, we'll scroll through, have a look at the answers. If there's any of those that you need to go over, then just bring it to my attention after we've seen all of the answers there. So questions 1 and 2, have a peek. Questions 3 and 4. Five and 6. I had somebody asking me just yesterday, actually, somebody cross country yesterday asking me about question number 6. How do you find acceleration? Well, bottom line is, if you got a force and you got a mass, you have a mass of the electron, all the separate particles of the data sheet. We'll then just use F equals ma. Right? You've got force, you've got a mass. Let's say A is equal to F over M. Solve for the acceleration. And finally, question 7 and 8. All right, we've got a request to go over 3, 6, 7, and 8 on that worksheet. Let's do that now. Number 3 says an electric force of 7.19 times 10 to the negative 8x between two charges, both of magnitude 2.0 times 10 to the negative 10 coulombs. So we're in coulombs, but clearly you can see that we've got a pretty small amount of charge, 10 to the minus 10 coulombs, which is pretty standard, right? We want to find the distance between the two charges. Here's a force, the magnitude of the force. Here's Q1 and Q2, both charges, and we want to find the distance that separates them. We want to find R. So our equation is, of course, our Coulomb's law equation that we learned about before I was absent yesterday. Got to rearrange that to solve for R, the distance that separates these two charges. Bring it up by multiplying. It becomes F times R squared. Take the F down by dividing. R squared becomes K Q1 Q2 over F. But of course, to get R by itself, what do we have to do, Daniel? Right, we got to square root that. So it becomes R is equal to the square root of K Q1 Q2 over R squared, and then it's going to look like this. So we got 8.99 times 10 to the 9. We got two charges, but they're both the same, 2 times 10 to the negative 10. You could square that if you want, or you could just say 2 times 10 to the negative 10 times 2 times 10 to the negative 10. We divide that by the force. And the force is, of course, 7.19 times 10 to the minus 8 newtons. And then we square root that. Who asked me for that question? Is that okay? Was it a rearranging thing, or what was the issue with it? Yeah? So you're good now? Next question, I think, was 6. Sorry? 6 says, and calculate the initial acceleration of an alpha particle. I give you the charge of the alpha particle on the sheet, but if I didn't, okay, even if you've never heard of an alpha particle before, where would you immediately go to find the charge and or the mass of the alpha particle? Simon's going to his data sheet. Good, that's exactly where you should go. Look, if you need data that you don't have, then odds are it's going to be on your data sheet. At least check there, right, to see if the charge, the mass, whatever is there. So we want to find the acceleration where we have a certain charge. We got a certain distance here. Let's see. We want to find the acceleration of the alpha particle and the acceleration of the electron. Okay. Okay, so we want to find two things there, right? Acceleration of the alpha particle and the electron. There's an electron here as well, so let's say that's Q1. Q2 would be the charge of the electron, which is negative 1.60 times 10 to the minus 19 coulombs. So we got two charges. We want to find the acceleration of both of them. Well, here's what we do first. Here's a rule of thumb, guys. In Physics 30, whenever you're asked to find acceleration, get the force, whether it's an electric force or a magnetic force or a whatever force, get the force, and then use F is equal to m times a to find acceleration. So the force that acts between this electron and this alpha particle is kq1 q2 over r squared. 8.99 times 10 to the 9 times 3.2 times 10 to the minus 19 times 1.6 times 10 to the minus 19. divide that by r, which is 2 times 10 to the minus 25. Don't forget to square that. We end up getting 1.1507 times 10 to the 22 newtons. That's the force that acts between the alpha particle and the electron. It's the force that acts on both the alpha particle and the electron. Now we want to find the acceleration on both of them. The acceleration is always given by the equation A is equal to F over m. The magnitude, that is, of the acceleration is the magnitude of the force divided by the mass. If you want to find the acceleration of the electron, then go 1.15 divided by the mass of the electron, which is on your data sheet. You want to find the acceleration of the alpha particle, then go 1.15, because it's the same force, divided by the mass of the alpha particle, which is also on your data sheet. So don't be afraid to check that data sheet. You misses something, go to your data sheet, because odds are it's going to be there. Simon?
So the equation, does it give you a charge for the electron and proton?
Yep.
You just assume it's multiplied by
Yes. Yes. In fact, Simon, you said if it doesn't give you a charge for the electron or proton, then just assume it's 1.6. Yeah, whether it does or doesn't give you a charge, it's going to be 1.6, right? The charge of the proton and the electron have to be 1.6 times 10 to the minus 19. The electron would be negative, but in most cases when we're solving a problem, that doesn't really matter because we drop the sign of the charge whenever we're plugging it into an equation anyways, right? Does that make sense? So when we go here, notice I didn't put negative 1.6, right? We okay there? Who asked me for 6? Good. Number 7 was the next one we need to go over. Here, this charge is touched with another one, both positive. Then with a neutral object, the first charge is then separated from the second charge. What's the electric force between the first and the second? There's quite a bit to work through here, right? There's one charge touching another, then another, and then another, and then we want to find out what the total force is. And quite a bit of work here. Let's find out what the charges are first. We got 3 charges, 1, 2, and 3. It's 2, 6, and 0. The first one touches the second one. So 2 and 6 becomes 4 and 4, right? 2 plus 6 divided by 2 is 4. So 4, 4, 0. Then it touches a neutral object. So the 4 and the 0 become 2 and 2, with the second one being 4. These are my 2 charges now, 2 coulombs and 4 coulombs. And now I'm going to say F is equal to K Q1 Q2 over R squared, where this is 2 coulombs, this is 4 coulombs, and this is 5 times 10 to the negative 2 meters. So now it becomes relatively straightforward mathematics there. Remember, when something touches something else, when a charge touches another charge, they want to balance, okay? And if you're not given any indication otherwise, then just assume that they do balance. Right? We said that, you know, there's always those times when you have one object that's way bigger than the other object, they don't balance out. When you have one object that's a different shape than the other object, they might not balance out. Okay, but unless you're given an indication that they don't balance out, assume that they do. So 1 touches 2, they balance. 1 touches 3, they balance. We're left with 2 and 4, and we just plug them into that equation. Lastly, on this worksheet, number 8, object 1 has a charge of 1 times 10 to the negative 5. 2 is negative 2. 3 is negative 3.5. 1 touches 2. 2 touches 3. 1 is brought away from object 3. What's the force that acts between 1 and 3? Another one of those questions where it's kind of a challenge just because of the amount of stuff that's in the question. No part of it, no single part of it's that crazy hard. There's just a lot in it. Okay? So let's draw the chart the same as we did in the last question, 1, 2, and 3. 1 is 1 times 10 to the minus 5. 2 is negative 2 times 10 to the minus 5. This is when we actually do care about the sign of the charge. 3 is negative 3.5 times 10 to the minus 5. 1 touches 2. All right, they balance out. 1 plus negative 2 is negative 1. Divided by 2 is negative 0.5 times 10 to the minus 5. Yeah, that's not actually in scientific notation, right? Scientific notation would be digit, decimal, digit, not 0 decimal, whatever. Why not leave it there, right? Why not leave it there? Okay, so what if it's not scientific notation? Okay, the third one is 3.5 times 10 to the minus 5. All right, 2 touches 3. Negative 0.5 and negative 3.5. We're going to balance it to give me negative 2 times 10 to the minus 5. And this one's going to remain negative 0.5 times 10 to the minus 5. All right, now we want to find the force between 1 and 3. So we're going to say, same thing as we did in the last question. Let's say KQ1, Q3 over R squared. Okay, 8.99. 0.5, drop the negative sign. 2, drop the negative sign there. And then R is going to be 2 times 10 to the minus 3. Just don't forget to square that. We plug the numbers in, and we should get our answer there of 2.25 times 10 to the 5 newtons. Right. Next bit of homework we had was 538, 1 to 10. Any issues with those questions on page 538, please? All right, we need 3 questions to go over here, 1, 2, and 5. 1 says identify 2 factors that influence the force of electrostatic attraction or repulsion acting between 2 charges, and write a mathematical expression to describe this relationship. This one's kind of one of those ones where it's like, what exactly are they asking? Once you know what they're asking, it's an easy question. What are the 2 factors that influence the electrostatic force? Well, the charges, the magnitudes of the charge, and the distance that separates them. Those are the 2 factors. Right? So how big the charge is clearly going to affect how big the force is. How far apart they are is clearly going to affect how big the force is. So write a mathematical expression to describe this relationship. We're going to say KQ1, Q2 over R squared. In other words, Coulomb's law. That's it. That's all they're asking there, right? Question 2, describe how the inverse square law, first proposed by Newton for gravitational forces, was applied to electrostatic forces by Coulomb. Well, there's not a great question even, because in the end, there's not really a big answer to this question. How is it applied to electrostatic forces by Coulomb? Well, Coulomb performed an experiment, right? Coulomb's torsion balance experiment, which found that the relationship between force and mass and charges is the same as the relationship between force and masses. He also found the relationship between force and distance for electrostatics is the same as the relationship between force and distance for gravity. So in other words, he did an experiment and found that it's the same relationship. Okay? And then he derived an equation that took the same form as gravity, and that's that. I don't think there's really more we can say really put down for that answer there, question number 2. And finally, question number 5. Oh, good question. Good question, number 5. Nice variable value changing question we have here. It says an electrostatic force of 10 newtons acts between these charges. But then we do some things. We make some changes. We change the value of variables without knowing what the values were to begin with. We double one of the charges, and then we double both of the charges. Well, for question A, my original force is KQ1, Q2 over R squared. You guys remember doing this in Unit 1, momentum? You had to do this on our unit test, right? And you guys did a good job on our unit test when you had to do this. Okay, 10 newtons. My new force for question A would be K times 2Q1 times Q2 over R squared. That becomes 2 times KQ1, Q2 over R squared. 2 times my original force, so it becomes simply 20 newtons. If we want to double both of those charges, well, my new force now, my original force, still going to be KQ1, Q2 over R squared, still going to be 10 newtons. My new force is going to be K times 2Q1 times 2Q2 over R squared. Well, that becomes 4 times everything we had. Sorry, that's not equal 10 newtons, though, is it? 4 times KQ1, Q2 over R squared. But we know this value is 10, so my new force becomes 40 newtons. We okay with that? All right, let me give you another one of these, actually, while we're on the topic of this question here. Let me give you another one that's a little bit harder than what we just did. Let's say we start off with the same stem of the question in question number 5. But instead of changing the charge on one sphere or the charge on both spheres, let's change the distance. Let's triple the distance. Okay, let's triple separation distance. Okay, I'm going to give you a couple seconds here to see if you can do that right now yourself. All we're doing is tripling the separation distance. What's the new force become as a result of that? All right, let's take a quick peek at it. Our original force, of course, KQ1, Q2 over R squared, also equal to 10 newtons. My new force, KQ1, Q2 over, we're tripling it, right? What did I say, tripling? Yeah. 3R. Oh, let's see. Anybody not get 3.33? Anybody else get something else? What are we tripling? What are we squaring here? Tell me what variable we're squaring. Okay, let's go back up to this equation right here. Tell me what variable we're squaring right there. This doesn't seem a very hard question, is it? Is it a trick question? What variable are we squaring? Yes, good answer. We're not squaring R. We're squaring the distance that separates them. Now, that just happens to be represented by R. But we're squaring the distance. Well, down here, we're squaring the distance as well. But what's the distance? The distance is 3R, right? We got to square the distance. We're not squaring R, we're squaring the distance. And the distance is 3R. So this becomes KQ1, Q2 over 9R squared, right? 9R squared, because we had to square everything inside those brackets. We had to square the entire distance. So it becomes 1/9 of my original force, which was 10 newtons. 1/9 of 10 newtons gives me not 3.33, but 1.11 newtons. Anybody get 1.11? Nobody? Oh, goodness. All right, I think we need to try another one of these then. Let's try another one that's actually a little bit harder even still. You guys, you understand why you're squaring the 3 as well as the R, right? Because Bailey said we're squaring the distance. She's right, 100% right. We're squaring the distance, and the distance is 3R. It's not R. Just happens to usually be R. That's usually the way we represent distance. But in this one, it was 3R. Okay, let's do this. Let's triple one of the charges. Let's triple Q1. We'll leave Q2 the same. And then let's cut in half. Not Q2. Let's cut in half R. What does the new force become? All right, my original force is still 10 newtons and still KQ1, Q2 over R squared. My new force this time would be K times 3Q1, because we're tripling the first charge. Q2 stays the same. R becomes 1/2 of R. But remember, we're squaring the distance. We're not squaring r, we're squaring the distance. So this is going to become, what do we got? On the top, it's 3. On the bottom, 1/2 squared is 1/4 times k q1 q2 over r squared. Right? Pull the 3 out front, square the half and the r. Pull the 1/4 out front. What's 3 divided by 1/4? 12. Good. If you're not good with fractions, well, I hope you are good with fractions. I hope you know that when you're dividing 3 by 1/4, it's the same as multiplying 3 times 4 over 1, right? Multiplying by the reciprocal. But if you're not good at that, use your calculator. Okay, divide by 3 divided by brackets 1 over 4 brackets, and you're going to get 12. So we get 12 times k q1 q2 over r squared. But of course, that's my original force, which is 10 newtons. So it becomes 120 newtons. All right, last thing that we need to go over here from homework over the last couple of days is worksheet number 7. Okay, put up the answers here now. 1A and B up there now. Okay, 1C and D up on the board right now. 2A and B on worksheet number 7. C and D. Question number 3. And question number 4. All right, let's take a look at worksheet number 7 here. Question 2A. We'll also do question 3 or 4 as well. It says 3 charges are in a straight row. And the first charge is a value of 2.5 times 10 to the negative 2. The second one is negative 4 times 10 to the minus 2. And it's 60 millimeters to the right of the first one. So let's draw that right now. 3 charges in a row. Let's call this number 1. Let's call this number 2. 60 millimeters to the right of the first one. We're going to want to make sure that we convert that to meters. The first charge is 2.5 times 10 to the minus 2 coulombs and negative 4 times 10 to the minus 2 coulombs. Then we got a third one that is 5 centimeters to the right of the second one. It's going to be over here, 5.0 centimeters. We're also going to want to convert that to meters. And it's positive 3.0 times 10 to the minus 2 coulombs. We want to find the net force on the first charge. Now, Simon, you were asking a question a few minutes ago. How do you know whether the force is left or right? Okay, we're going to look at charge number 1 right now. Okay, in the example that I showed you a minute ago, we were looking at the second one. Doesn't matter, though. Look at the first charge. Now, pretend the third charge doesn't even exist right now. We want to find the direction of the force between charge 1 and 2. Then we'll deal with the third charge later on. 1 and 2 are oppositely charged. That means that they attract each other, right? Opposite charges attract. That means that 1 will be pulled towards number 2. We're going to call that the force of 2 on 1. Okay, 1 is pulled towards 2. Does that make sense? Now, 2 is also pulled towards number 1, right? But we don't really care about that because that's not the force we're trying to find in this question. Now pretend 2 doesn't exist. We're looking at 1 and 3 now. 1 and 3 are like charges, so they're going to repel each other. That means 1 is going to be pushed away from number 3. We'll call that F31, the force of 3 on 1, to the left, away from number 3. Now, 3 is also going to be pushed away from number 1, but we don't really care about that because that's not the force that we're trying to find. So in the end here, the force is acting on number 1. We've got 2 of them. One of them's to the left, one of them's to the right. We get both of those values, and once we get both of those values, it becomes just a matter of adding them up, but ensuring that we make one of them, F31, a negative value. So let's get both of those forces now. Let's say the force of 2 on 1 is K Q1 Q2 over R squared. Make sure you make R here, not 60 millimeters. Make sure you make R here 60 times 10 to the minus 3 millimeters, or 0.060 meters. And don't forget to square that. Okay, we plug in our numbers for the value of K in Q1, and Q2, dropping the negative sign for Q2, divided by 0.06 squared, gives me a force there of 2.4972 times 10 to the 9 newtons. Okay, we'll do the same thing for F31. This one's a little bit trickier though. KQ1, Q3 over R squared. Okay, we got K, we got Q1, we got Q3, but R this time isn't 60, it isn't 5, it isn't 0.06, it isn't 0.05, but rather that distance is 0.11 meters. Where does that come from? Anybody explain to me where that 0.11 meters comes from? Caitlin? Right. If you want to find the force between 1 and 3, you need the distance between 1 and 3, which is the sum of this and this. Put them both in meters, add them up, 0.11 meters. Okay, we get the force there. It works out to be 5.5723 times 10 to the 8 newtons. Now, we got to add them up. But when we add them up, F31 becomes a negative value. So it becomes 2.4972 times 10 to the 9 plus negative 5.5723 times 10 to the 8. And when we add those up, we end up getting 1.94 times 10 to the 9. Is that okay? Simon, does that make sense, sir? All right, now the next question that we'll do, we'll have a look, say, at number 3. Not dramatically different. It seems a little bit different when you see the solution, but the way that we think about it is real similar. Okay, in the end, we have to draw a free body diagram. In the end, we have to identify which way the forces go, and we have to calculate the individual forces, just like we did there. The only real difference between question 3 and question 2A, say, is the way that we add those forces up. When they're in one dimension, we can add them up just like that. When they're in 2 dimensions, we have to draw a vector diagram and add them up that way. A little bit more work, but not really that much harder. So it says repeat question 1B, but with a third charge below the second charge. So the diagram is going to look like this. If you go back to 1B, put the third charge below, the diagram is going to look like this. 1, 2, and 3. 2.5 centimeters is the distance between 1 and 2. We had 2 centimeters, the distance between 2 and 3, but in a different direction this time. Positive 5.00 times 10 to the minus 5. This one is also positive 5.00 times 10 to the minus 5 coulombs. And charge 3 is negative 2.50 times 10 to the minus 5 coulombs. We want to find the force on the second charge. So let's draw a free body diagram for the second charge. Same thought process we go through for the last question. Forget about number 3. Pretend it doesn't exist right now. 1 and 2 are both positive. That means they're going to repel each other, right? They push each other apart. 1 pushes 2 to the right, the force of 1 on 2. Now, 2 pushes 1 to the left, but we don't really care about that because we're not trying to find the force on number 1. 2 and 3 are oppositely charged. One's positive, one's negative. They attract each other. 2 is attracted toward number 3. We'll call that F32, the force of 3 acting on 2. Right? 3 pulls 2. Now, there's also a force that's towards number 2. Right? Number 3 is pulled towards number 2, but we don't really care about that force because it's not the one that we were asked to solve for. So we got 2 forces here, F12 and F32. Now, you've already calculated both the values of those forces because the distances and the charges are the same as they were in question 1B. When you calculate F12, it worked out to be 3.596 times 10 to the 4, just like it was in question 1B. F32 worked out to be 2.809 times 10 to the 4 newtons, just like it was in question 1B. Now, though, when we add them up, we're not going to do it like we did in 1B. We're not going to say 3.596 plus 2.809, make them negative if they have to be. Now we're in 2 dimensions, so now we've got to redraw this as a vector diagram. 3.596 times 10 to the 4 newtons, 2.809 times 10 to the 4 newtons. And then the resultant vector is right there. That's what we're trying to find out, right? The resultant force there. So this time to get F, instead of just adding them together, this time to get F, we've got to do the Pythagorean theorem. The square root of 3.596 times 10 to the 4 squared plus 2.809 times 10 to the 4 squared. When we do that math, we get 4.56 times 10 to the 4. And the angle that we get there, found by the inverse tan function, always the inverse tan, right? Of opposite of our adjacent. Ends up being equal to 38 degrees. How many people got that? Are we okay with that? Do you think that those questions where we're in 2 dimensions are any harder than the questions where we're in 1 dimension? Like, really, the only thing you got to do in these questions that you didn't have to do in the other questions where it was 1 dimension is this, right? Instead of just adding them up, one positive, one negative, or both positive, we got to draw a vector diagram. Do the Pythagorean theorem. Okay, Pythagorean theorem is what, grade 6, grade 7 math? Okay, so really the only difference between this question and the last question is grade 7 math.